Hi guys, today we will cover development length in concrete. The first question, what is development length? So development length in concrete refers to the minimum length of reinforcement rebar that must be embedded or anchored into concrete to develop its full strength and safely transfer stress between steel and concrete through bond. So here you have some primary steel for beam, then you have again in both zones, and you have development length. That means that we need primary steels from beam to beam embedded into column in order to prevent failures in concrete. So development length is the length of the rebar needed to transfer the tensile force from the steel to the surrounding concrete without slip or failure. To ensure proper bond between steel and concrete, to prevent pull-out failure, and critical areas of high stress such as beam, column, joints, supports, and splices. So firstly, for tangent development length, we have basic equation using ACI code 25.4.2 and 3 and the ACI equation 25.4.2.2. Again, we have a compression development length using ACI section 25.4.9. So the first, we will cover the basic equation, and we have some equation LD which depend on type of concrete. If we have normal weight concrete, lambda will be 1. If we have lightweight concrete, then we will use 0.75. Then we have compressive strength of concrete, which is given as FC prime. Then we have yielding stress. And what we can notice in this equation, we have some confinement term for bar location, epoxy coating, and size of rebar that is given in ACI table. dB will be the diameter of rebar. So these terms CT, CE, and CS you can find using ACI table. So again, we have some CB plus KT gamma over dB, that is a confinement ratio, and it is less than 2.5. So for CB, we are using minimum of distance from concrete surface to the center of bar, or half of center to center spacing of rebar. How to find KT gamma? That is 40 times AT gamma over S times N. So what is AT gamma? That is area of stirrups, or we can use AV, what we used in previous chapter. S will be spacing of stirrup, and we have N as anchored rebars. So this is simplified equations for development length. For number 6 and smaller bars and deformed wires, we are using equation Fy times CT times CE over 25 lambda times square root of FC prime, and we are multiplying that with the rebar size. If we have number 7 and larger rebars, instead of 25 lambda, we are using 20 times lambda. This is case 1, when we have clear spacing of bars or wires being developed or lap spliced, not less than rebar diameter size, clear cover and stirrups or ties throughout development length, not less than the code minimum, or clear spacing of bars or wires being developed or lap spliced at least 2 times diameter of bars, and clear cover at least dB. In all other cases, you have different equations. We need to multiply with 3 the first term of the equation and to divide by 50 times lambda if we have number 6, and for number 7 and upper bars we have 3 and 40. So this is the table which I already mentioned. This is modification factor for lambda. We said we are using 0.75 for lightweight concrete, and for normal concrete will be 1. And then we have these terms Psi, which is epoxy. And now we have different conditions. For instance, if we have uncoated or zinc-coated galvanized reinforcement, we're using 1. For Psi-S, that is a size for number 7 and larger bars, we are using 1. Other case is 0.8. And casting position, if we have, for instance, more than 12-inch of fresh concrete placed below horizontal reinforcement, we are using 1.3. And in all other cases, you're using 1. So you will see what is given in your problem and how to determine all these modification factors. If we have a development land in compression, then we are using 2 equations, the maximum of the 2. The first one will be again yielding stress times, now we are using some factor Psi-R, and we are dividing everything with 50 times lambda square root of Fc prime, and all of this we are multiplying with rebar diameter size. And the other equation is 0.003 Fy, which is again yielding stress times Cr times dB. So what is Cr? That is confining reinforcement. And again, you have several conditions. For instance, here it is given reinforcement enclosed within a spiral. Then we are using 0.75, or number 4 bar or D20 wire ties in accordance with 25.7.2. Again, we are using the development length spaced less than 4 inch. Again, we are using 0.75. In all other cases, we are using 1. This is how to determine the hooks in tension. Again, so development of standard hooks in tension, you need to find LDH. Again, you have 3 equations, and you can notice that these terms Psi, Psi, and Cr is given. And again, you have here some table 25.4.3.2. This is modification factors for development length of hook bars in tension, and depending on your condition, you will determine your values. And again, you have here for B 8 times diameter of bar, rebar size, and you have 6 inch, so we are using the maximum of the 3. So we mentioned earlier that we have 90-degree hooks and 180-degree hooks. We have 135 also. 90-degree hooks we are usually using for non-seismic conditions, and 135, 180 for seismic condition. Again, you have some bar size, and you need to find minimum inside band diameter in inches. Again, you have different depending on the bar size. For 90-degree hooks, here is a straight extension. How to determine L extension, here it is given on the picture. And you have for 180-degree, this is again table 25.3.1. This is ACI code. Then you have example. I did one example regarding to this case, how to determine development length if we have 3 number 8 rebars. So for in this case we have tension rebar 3 number 8. We have stirrups, it is given to us number 3 at 8 each distance. Bottom cover is 3 inch, side cover 2.5, compressive strength of concrete 4000 psi, and you have yielding stress 60,000 psi, cross section 11 inch by 18 inch. So firstly, we need to determine tension development length. Let's do firstly ACI simplified equation. So we are using table 25.4.2.2. And since that we have number 7 and larger bars, we are using equation Fy times Ct times Pce, and we are dividing by 20 times lambda square root of Fc prime times dB. So clear spacing in this case will be the end of diameter of the rebar and the end of the next rebar. So in this case, it will be 3 minus 2 times diameter of the rebar size divided by 2. That will give me a clear spacing of 2 inch. Clear spacing between bars, rebars is 2 inch. So since that clear spacing is higher than diameter of the rebars, clear concrete cover is 3 inch minus half of diameter of the rebar number 8 minus stirrup size, and in this case that will be 3 minus 0.5 inch, and stirrup size for number 3 will be 0.375. So in this case that is 2.125 inch, which is again higher than diameter of number 8 bar, which is 1 inch. So now to determine what is the development length, so using the equation given in table 25.4.2.4, we have normal concrete 4000 psi, that means our lambda is 1. For yielding stress, it is given for us 60,000, and CT is 1, CE for uncoated bar is 1, and when we plug our values in the equation, we'll obtain that our development length is 47.43 inch. This was the first approach using simplified ACI equation, but if we are using basic equation, we have again equation 3/40 times lambda. Then we have a yielding stress, we have FC prime, square root of FC prime, and again we have some CT, CS, and CE. And we said here that we will have a term CB plus KT gamma over DB. And in this case, we have 1.5 plus 0.366 over 1, which will give me 1.866. That is less than 2.5, and CB will be minimum of the two. This is distance from concrete center bar to the nearest concrete surface. We calculated that to be 2.5 inch, and half spacing between rebar, which is 1.5 inch. That's why we are using CB here in the equation 1.5. Then what we have here, how to determine KT gamma, that is 40 times area of the stirrup, which is 2 times 0.11, since that we have 2 legs and we have number of 3 stirrups. Again, we have 40 times 0.22. Spacing of stirrup is given to us to be 8 inch, and we have number of anchored rebar, which is given to be 3. So that is KT gamma 0.366. And if we plug our values, we will obtain the development length using the basic equation is 38 inch. So what we have, if we are using simplified equation, your development length is 47.43. And if we have a basic equation, we have 38 inch. So that is, we will determine that the minimum value of the two is 38 inch. So what we have here, we need LD to be higher than column size. Our column size is 22 inch, and that means that we need to provide hook. And using the section 25.4.3.1, our value for the hook will be maximum of the 3 equation. So since that we have rebar size of 1 inch, our 8 times dB will be 8 inch. We have 6 inch that is given to us according to ACI code, and we are using equation Fy times CE times CC and times C gamma. So in this case, we are using table again 25.4.3.2, and all of these terms are equal to 1, so our LDH is 19 inch. Using the table, again, we are going at the beginning, ACI code 25.3.1, we will select 90-degree hooks. So this is table 25.3.1, and we have bar size between 3 and 8 to be 6 times dB. And now your minimum inside band will be 6 inch, extension will be 12 times rebar size, which is in this case 1, so that is 12 inch. So if you need to show me this picture, so again you have extension of 12 inch and you have inside 6 inch, and again LDH will be the maximum of the three.